Good afternoon. On behalf of Engineers Australia, I'm delighted to welcome you all to our Thought Leaders series, Managing Engineering Assets Through Simulation and Integrated Modelling. My name is Govinda Pende and I'm from Engineers Australia. Firstly, in keeping with our customs, Engineers Australia acknowledges the traditional owners of the land and recognises their continuing connection to land, waters and community. We pay our respects to their cultures and to elders, past, present and emerging. Before we get started today, I would like to acknowledge that today's webinar is being hosted with Engineers Australia's industry partner, QUT, Queensland University of Technology. QUT is a major Australian university with a global reputation and a real-world focus. Its courses equip the students and graduates with the skills they need for the world of today and tomorrow. They are an ambitious institution with a rapidly growing research output focused on technology and innovation. The Times' Higher Education 2020 ranked QUT in the top 180 universities in the world and the best young university in Australia. Their strategic plan, Blueprint 6, establishes QUT as the university for the real world and charts its provision of transformative education and research that is relevant to our communities. With approximately 50,000 students, QUT places a premium on the national and international accreditation of all professional degrees. They do offer academic programs in fields spanning business, creative industries, education, engineering, health, law, science and social justice across 5 faculties. Well known for their strong links to industry and government, the high impact of their research, which involves multidisciplinary teams, can be seen across areas as diverse as climate change mitigation, digital media, materials science and biomedical innovation. Now today we will hear from 3 speakers followed by our live audience Q&A session, and I would encourage you all to send through your questions to our speakers via the YouTube chat box during the presentations today. I would now like to welcome our moderator for today, Associate Professor David Holmes. David is an Associate Professor in Mechanical Design and Manufacturing at Queensland University of Technology. He holds a Bachelor of Engineering Honours in Mechanical Engineering and a PhD in Computational Mechanics from James Cook University, specialising in the development and implementation of numerical simulation algorithms. His current research centres around the development of multi-phase, multi-physics numerical simulation software for application to a wide range of problems, including flows through porous media and biomedical research. Dr. Holmes also works on the development of new image processing methods for biomedical geometry recognition, the development of programmatic frameworks for the deployment of physics applications on parallel hardware architectures, and a range of pedagogical developments in higher education. Please welcome David Holmes.
Thank you, Megan, and welcome again to our viewers. So firstly, I'd like to welcome our first speaker, Emeritus Professor Lin Ma. Professor Lin Ma focuses on engineering asset management as her main area of research. Professor Ma's collaborative work with colleagues both at QUT and at other institutions has attracted over $3.3 million in competitive research funding. Whilst being involved in various research projects throughout her career, Professor Ma's teaching covers a broad range in engineering, from manufacturing systems, operations management and traditional industrial engineering to the more contemporary disciplines of engineering management and asset management. Professor Ma has been awarded Queensland's Smart State Smart Woman Award in 2007 and QUT's Vice Chancellor's Award for Excellence in Research in 2007 as well. So please join with me in welcoming Professor Lin Ma.
Thank you, David, for the introduction. Good afternoon. Welcome everyone to this workshop. Today I want to talk about integrated engineering asset management research and application, which is very important for getting the digital representation of your asset management in your own organization. This is our QT research team in asset management. And we also have a number of PhD students and master students. Below are those industry organizations we are collaborating at the moment to have a research project. QT has a long history in the research in asset management, starting with the CRC for Engineering Research Management, which is a SIME from 2004. So that's over 15, 16 years already. So that's our team. We developed integrated asset management decision support framework that is accumulation of many years of research. You can see there are different layers of this framework, starting from data and data management, data analysis. Now people use big data, so this is a lot of related to big data technology. And then you have condition-based prediction layer. That is when you have condition information like condition monitoring and other information regarding your asset, especially at the base, we call that the base maintenance unit, which is a component level. And then you can have condition-based prediction for those units. And then you have to go up to system integration to look at how system is working for your business. What is the best way to manage your system? And then you have a business integration layer where your asset is generate value for your business. What is the best value generation format? And then decision support layer. That means where you have optimized decision, when you make the important asset decisions, they always involve many aspects of the business and many factors that are correlated. So it's a complex problem to solve. So normally you need optimization models to help you to make better decisions. So decision layer is another layer where you can have lots of simulations and calculatings. But when you implement integrated asset management in your organization, I would suggest you starting from top level, which is identify important critical decisions for your business regarding your assets, so that you can identify the information and the knowledge you need for those decisions. And then you can look at how those system model could be developed to provide those information and the knowledge. And then how the component level, the conditions, the health of the component and system could affect those decisions. So then you can identify the data you needed. So that's a top-down process, but in the process you could have bottom-up, top-down. So that's the things I would suggest, that in the beginning of the process you understand what critical decision you need to make. Data issues is always very important for engineering asset management. We all know that. From our experience, in asset management, especially when you do the predictive model, your problem is not the big data. It's actually small data, because regarding to failure mode, regarding to the health degradation process, the useful data actually is very small. That means you haven't collected the right data. Most of the data people collect are useless in our experience. I don't know about yours. So we really need to have a good model, good research approach to deal with highly truncated data and incomplete data, especially lacking of failure mode data. And we have to be aware that the health of asset and the failure of the asset are very different. And you have to use a different data, different modeling approach as well. And also you have a very different data, like a small size, a big size, more frequently collected size, and less frequently collected size, discrete data and continuous data, useful and useless data. A lot of data useless, right? So we need to deal with all those problems. So during the last 15, 16 years, for dealing with those problems and dealing with the different aspects of integrated asset management, we developed a lot of algorithms that actually are applied to industry. And that means that we have accumulated a lot of learning curves so that we don't need to start from zero when we take the new project. We know that when we deal with the industry, normally they need a solution yesterday. So you don't really have a lot of time to start learning your research and to deliver the result. So this is something we developed and we would like to share with everyone. So that is basically integrated engineering asset management. So I want to talk about the research modeling approach that we have for the health prediction of different assets. I give you a couple of examples because our time is very limited. One example is industrial boiler, the heat exchanger in those industrial boiler. So we have came across some of those similar assets in power generation industry, and this particular one is in process industry. And those tubes of those heat exchanger working in a very, very dynamic environment. Thermodynamics, particle dynamics. There are particles in gas erode the tubes, and there are different pressures, flows. So it is difficult for people to inspect, especially when those production is in peak time. So they do need certain predictions into the erosion of the tubes and the health state of the tubes. So we developed different modeling approach. One part is a physics model, which use numerical simulation to simulate the dynamic situation within the boiler so that you can predict the thickness of the tubes under different conditions. And then we have a data-driven model, like a big data and an AI model, to look at what are those failures could happen, probability of those failures could happen at a certain area or certain panels, and when would the burst will happen. And then you can look at use those information to guide your decisions on maintenance, especially to predict what is the best time to renew your assets. So this project is basically asking us to look at their capital plan. That means the budget plan. And we all know that our budget always is limited. How to the best to use our money. To do that, we need to understand the health condition and degradation process of your assets. So this is the prediction result we achieved using both physical model and the data model, data-driven model. And you can see the result, use the past data to test the model is pretty good. And then how to support your capital decisions, we needed to use a cost model and to consider the seasonal productions for that particular application and a lot of other safety dynamics. And then the project focused on the 224 capital budget items. As a result, we could deliver 5.5 reduction into company's existing capital budget. Each company has your capital budget for next few years. So that's the result of the integrated modeling of asset management from the data to predict of the health condition and to involve business modeling, integrated business modeling, and then to achieve the decision support. Another example I want to give to you is electricity transmission network. We define this type of asset as a linear asset. It's not an individual asset. Linear assets have different characteristics. We have done different linear assets like water network, water supply pipes network, and railway tracks network. And this is a power transmission, electricity transmission. We know that the power transmission network have very few failures. You're not allowed to fail. So it's very difficult to model the health condition and the maintenance works. So we figure out how to overcome these things using a parameter called MTE, which is maintenance trigger event. They have a very good record of past maintenance record. And then we filter the maintenance record with more failure related and capital related. And also the network, the health conditions, the conductors, they degraded at a different rate. Depends on the different environmental factors. For instance, there are conductors near the coast, in the city, or above the plantation. So they all sort of perform differently. So as a result, the prediction I show you is really just twisted information because of all the confidentiality. One is 5 years prediction. The blue and the light colors means less maintenance. And then the orange colors more serious. So in 15 years, there are some sectors of those network could have some serious maintenance. So that's the sort of the things we do. We're dealing with the data, very limited data into the failure and also to different assets. Another thing I want to mention is system functional reliability prediction. This is a new approach one of my PhD students developed. We all know that the system reliability is very hard to predict, especially your system is complex and have a lot of interrelationship between different parts of the system. So this approach we use hidden mark model for component level or base maintenance unit level, and dynamic Bayes model for the system. And the advantage of this new modeling approach is that we use system functional reliability, system performance. And then we can predict the system business or performance, or physical performance over time. Use that to infer the conditions and states of different components within the system, use Bayes network. And even though we probably don't have a continual condition monitoring for each component or each part of the system, but we still can have prediction of those components because our modeling approach using different methods for like a hidden market, you don't need a lot of condition data. And also we also deal with the issue that the incomplete failure information of the system and the components. So there's approach actually can overcome a lot of those deficiencies. And we can use external covariates, so variables, for that impact into component degradation. So I give you some examples. Our researcher approaches we accumulated in last 15, 16 years, and then we could get onto a lot of different industrial application cases very quickly. And if you would like to implement integrated asset management, we would love to help. And also you can follow the framework to identify the things you need. For the asset management in the digital era, I give you this picture. Basically, look at different life stage of the assets and what is needed at a different stage due to the limitation of time. I just give to you so that we can discuss later. Okay, the conclusions. Integrated asset management research is very important in the digital era, and to improve scientific confidence of the predictions and the information, decision information. But most data are not ready to use from most of the industry cases. So we need to have a good approach, and only big data approach is not enough. It's not sufficient because lots of cases we only have small data. So we need smart modeling, collaborations. We need a lot of collaborations. Like in the Asset Institute, we collaborate with the industry and with the software developers like Dongsan, who will do the presentation later, and other IT companies. And so that we can work together to provide solutions to different industries. Thank you very much.
Thanks, Lin, for your excellent insights. So moving on, I'd like to welcome our second speaker, Dr. Govinda Pandey. Dr. Pandey has 25 years of international experience, both in industry and academia, and he works very closely with the universities, educational institutions, progressive businesses, and fellow civic leaders to help shift paradigms, transform societies, and inspire future generations of leaders. So please join with me in welcoming Dr. Govinda Pandey.
Thank you for the introduction. Let me start with a very brief introduction of Rockfield. Rockfield, we've been around for 21 years now, and we're spun out of James Cook University. We're quite established in mining and public infrastructure industries, and with a very strong collaborative relationship with universities and research organizations. So when we started Rockfield in early years, we were working in the engineering simulation space. So we were working on mining equipment, process equipment, bridges, railway fasteners, and we were working with the clients both nationally and internationally. When we started, we brought in the technology from the UK, the finite element modeling codes. We're making quite an impact in the area that we were working in. But then in around 2013, the mining downturn hit us really hard because we had a pretty sizable exposure to the mining industry. Then we started thinking about how we leverage the skills that we had to try and solve the pressing industry challenges. Then we started looking into this the aged infrastructure around us. So if you look at the Sydney Harbour Bridge, the most iconic structure of Australia. So the Sydney Harbour Bridge would be the age of Sydney Harbour Bridge is around 100 years at the moment. So generally, we design our structures for 50 and 100 years. So what is life after the end of the design life? And then if you look around in the built environment, we've got buildings, structures, towers. A lot of them are getting close to or past their original design life. So essentially, the challenge is with the trillions and trillions of dollars worth of aging infrastructure. And every now and then, some structures collapse. So this was the Morandi Bridge that collapsed a few years ago, tragically killing 30 people. And even in Australia, so we've got some challenges with the integrity of our structures. When you look at the Opal Towers or Mascot Towers, and there's still a few popping around every now and then. And there are other things in Australia and overseas. Structures do fail every now and then. But the structures, interestingly, or sadly for that matter, so they don't have any smarts. They've got nothing in there that can communicate with society around their health state, other than sort of the regular engineering inspection that is carried out on a periodic basis. Then we had a look at the whole Industry 4.0 revolution. So everyone is talking about the Internet of Things, the AI, and robotics, and all those sorts of things. And sort of the industry that we are in, particularly the infrastructure industry, is very much sort of been a laggard in adopting that technology. And sort of then we started thinking whether we can imagine putting a digital skin on infrastructure so that they can start communicating with us. And just the analogy that we tend to make is when you compare things in the Roman era and right now, sort of back then, so we had bridges as well. So, but mainly they were there for horses and carts. But now, sort of coming to 2021. So if you look at the automotive industry, the cars that we drive these days, sort of essentially they can sort of almost self-drive. They're packed with technology. But when you look at our infrastructure assets, for example, bridges, from the intelligence side of things, they were unfortunately dumb back in Roman times, and they are the same. Even right now, so certainly that we just need to change that. So that sort of inspired us to actually embark in a bit of a journey. Obviously, we are a consulting engineering company, so we've sort of leveraged our existing knowledge, but we've sort of got to create the new knowledge. So to do that, we've started actually collaborating with universities, and our actually first collaboration in this area was actually with QUT. We started that one in 2013 as part of the Enterprise Connect program. So we embedded a postdoc researcher into Rockfield. And then sort of after that, we thought that it's now important to actually include business analytics as well as data analytics. So in 2014, we started collaborating with Data 61. And then sort of gradually we started implementing the technology by working with lead users in both public infrastructure and mining space. And sort of towards 2017 and 2018, we actually started working in the Internet of Things space using the power of low-cost sensors in that. And in around 2019, sort of we developed a low-cost sensor technology, particularly for the utility industry application. And as a result, we spun a new company off called Lixia, which I'll get to in a little bit. So I'd like to share you a couple of case studies. The first one is around old railway bridges. So the challenges with these bridges are they were sort of designed 100 plus years ago, not for the modern day loading, and these steel structures degrade over a period of time with corrosion and all that, and fatigue is always an issue. And the design standards they keep moving or developing over a period of time. And when you look at these assets through the lenses of modern standards, it's unlikely that they pass. They meet all the requirements. So the traditional way of doing that one is using simple modeling techniques. But the problem with that is if you do that, then all of a sudden you see a lot of members being non-compliant. So we then used our modeling skills to actually take that one to a higher tier assessment. And if you look at the load path in these structures, it's really complicated. So in this instance, sort of we took it to a very advanced level in terms of modeling, and also some of them got corrosion issues and all that. So it's important to build that one into your model, and sort of we used as is condition to incorporate the current state of the structure into the modeling. And the challenge with advanced modeling is you've got to find a way to validate those models. So getting field data through bridge instrumentation is critical. So it's been through that process as well, just to collect the data, do the load testing and model validation. And as a result, what you've got is a digital twin that you can utilize to not only to understand the risk profile of the assets, but if there is a change in loading pattern or any sort of strike or impact events, then you've got your digital twin available to assist in making the decision. So the second case study I've got is on Sir Leo Hilton Bridge, commonly known as the Gateway Bridge. So obviously it's an iconic bridge as a concrete structure. The old bridge was opened in 1986 and it was duplicated in 2010 with 300 years design life, and over 110,000 vehicles cross that bridge daily. So essentially a very critical piece of infrastructure. So we implemented a structural health monitoring system into that bridge. This is a collaborative project, and the system is that sort of you put sensor network into the bridge, and through comms you then sort of transmit data to a cloud instance. You process the data, do the data management, run your analytics. And then sort of the application then for the end user is a cloud-based visualization platform that provides structural health monitoring insights in terms of anomaly detection, any indication on structural changes, and the data that's useful for predictive maintenance and providing operational confidence. To start that process, final element modeling was carried out to work out the load path and to identify the critical locations for instrumentation and sensor locations. So this slide shows the locations of the sensors, and this is just the result of the effect of the loading events. And this third wave is for a much bigger live load. So essentially, the process is, you sort of capture traffic behavior by using sensors and use the machine learning model to generate a health score for damage detection, so that the asset managers would get a live dashboard to see whether the health state of the structure has deteriorated or not over a period of time, and use that information to manage the assets. So this is a collaborative project. Obviously, Transurban is the asset owner, and Data61 is the lead solution provider, and University of New South Wales was involved in the modelling work. Cisco was involved in providing communications, and Rockfield was involved in the overall system design. And this project actually won the ITES Australia National Award on smart transport infrastructure. So the third case study I've got for you is on poles and wires. So if you look at the utility poles and wires in Australia, we've got 7 million poles, and those poles are to be manually inspected every 5 years. That's the regulatory requirement. But these poles, particularly the timber poles, it's a very hard asset class to manage because obviously they rot, they get attacked by termites, and a lot of them they're aging, and the unassisted failure of these poles are becoming more and more common. And the problem is the lack of real-time data that we've got at the moment. Maintaining and managing these assets are quite expensive, and obviously the innovative approach is needed to address that. So once we recognized this problem, Rockfield collaborated with James Cook University and utilized the Innovation Connections program through Oz Industry to really start working on a solution, Internet of Things based solution on that, and we're supported by CSR on program as well as from Safety Culture, and through that collaboration we spun off a new tech startup called Lixia. Lixia stands for Living Infrastructure by Informatics and Analytics. So what we've done is we've developed an Internet of Things device that you can see on your far right-hand side. And sort of it is essentially a pole top sensors. So once you attach that one towards the top of the pole below conductor lines, it will look for tilt, pitch, and roll of the poles. And also it looks for the sag of the conductor line. And these devices are wireless, and they're solar powered and reasonably low cost. And once you have these devices on your utility network, then you'll be able to obtain the data real time to be able to manage these assets. So we completed a proof of concept trial, which was successful, and then sort of now we're currently working on larger scale rollouts across Australia at the moment. So another thing that we realized by sort of going through this process is that even though you put those pole top sensors for structural information of the asset integrity of the poles, but given that it is there and that the sensors got the microclimate sensors as well as LiDAR sensors, it can also capture all the adjacent data, the data around the microclimate, the data around the water over road. And all these information are quite useful in smart cities applications and applications around sort of disaster management, around agriculture, biosecurity, education, and so forth. So essentially, like once you've got the Internet of Things devices, the potential of that is really, really large, and you're only limited by your imagination with the sort of things that you can achieve through these technologies. So now to conclude, so we've got both challenges and opportunities ahead of us. So the major challenge for us now is around climate change. As a society, we got to get to net zero by 2050, if not before. And with the CO2 emissions, it's all sort of going up at the moment. But not only we got to bend the curve, but we got to bring it down to zero. But at the same time, we've got opportunities. We've got the power of technologies with us at the moment. So now this is great opportunities for engineers, current and emerging, to really leverage that and make a difference. Thank you very much for your attention.
Thank you, Govinda, for your insights. That was wonderful. So moving on to our third speaker, I'd love to introduce Don Sands. So Don founded Synengco in 2001 with the aim of systemising decision-making in dynamic industries to enhance resource sustainability. He believes it is important to live well within our means, having a great standard of life whilst bettering our ecological footprint. Don has over 25 years of experience in operations and asset management in the power generation industry. His development of sentient system for asset optimisation has seen both environmental and financial benefits for his customers. So please join with me in welcoming Don Sands.
Thanks, David, for the introduction. Today I'm going to present to you about interoperable digital twins for whole-of-life asset management, and that's obviously part of simulation and integrated modelling. A bit about myself. I'm the founder and CEO of Synengco. I'm a board member of the Asset Institute, which is heavily involved with development of new technologies for excellence in asset management. I'm also a board member of Mimosa, which is open interoperability ecosystem for asset-intensive operations, and I'm a member of the Australian Standards for Automation Systems and Integration. I've had 30 years experience in asset management, and I'm the driving force behind Sentient System, which is a software solution for advanced asset performance management and optimization. So to introduce the concept here, I guess we're all going through this digital revolution, and it's no different from other industrial revolutions, if you like. So if we think about the first industrial revolution, there was new technologies, there was new fuels like coal and liquid fuels. There were new machines like steam trains and cars, new systems. We had to be able to refuel our cars, increased communication and increased application. For digital revolution, the only difference is really it's about new digital technologies and the new digital fuel, which is data and knowledge, new digital machines, new digital systems, increased communication and increased application. Now, when we think about the digital revolution, there's lots of elements within that digital revolution. There's robotics, big data, artificial intelligence, ubiquitous sensing, always connected, simulation and digital twinning, CAD/CAM, VR and AR. Today, we're talking about simulation and digital twinning. But if we look at this drawing here, we can see that there's actually only two interfaces into the real world. There's the sensing, where we're sensing what's going on in the real world, and there's potentially robotics, which is associated with taking action in the real world. There's also an element here, which is having the human in the loop. When we're talking about where we are in this digital revolution, we've pretty much gone through the information age, the collective intelligence, and now we're in that reputation age, where it's all about trust. Can I trust my digital systems? Can I trust my AI? Can I trust how someone has actually gone about building my systems? So when we talk about digital systems or advanced digital systems, we like to think of it like digital gaming. So I need to actually plan how I want to be able to operate my operation in a digital environment. So when we talk about a digital first strategy, we think about the game design. And when we're thinking about game design for asset management, we need to think about how we would design that game right through from a concept, through a detailed design, through the construction, through the commissioning, through the operation and maintenance, and ultimately at the end of the day, the decommissioning of that particular thing. So within the game design, we've got all sorts of tools available. We've got gamification, serious games, digital twinning, decision support, real-time optimization, simulation, scenario playing, and scenario learning. And the key to those from our perspective is having this simulation engine, which is really a digital representation of my actual operation. Now, to maintain a simulation engine for an entire operation is very difficult So we have to put AI and intelligence around how we actually can build this simulation so it represents a real plant. So there has to be some sort of self-learning capability in there. We have to have trust that that simulation engine does actually represent our real world. And then once we have that trust, we can actually predict how we expect the real world to go based on the simulation. The important part here is once we have it in a digital form, we can actually use it to do innovation. So we can, in the environment where we have safety, if you like, because we're not touching the real plant, we can go and try out new innovations with that simulation engine. So it becomes a tool for us to actually go and try new things. We can also use machines to actually optimize it. So we can try new things automatically with a digital machine doing that work for us. The other thing from a game type of aspect is the new generation is very familiar with working in a digital environment. And so you've already got that ability to see what's happening and being able to play the game. And so if we can apply that to asset intensive operations, we should be able to get a much better outcome because we're leveraging on the experience of the younger generation, plus also leveraging on the technologies that are available to give us that self-learned simulation of an actual operation. So taking it back to asset management, there's an ISO standard that's been developed which is around a digital twinning for asset intensive operations. And what they talk about is the secondary business process. So the primary business process is the value chain, if you like, from converting resources into something useful for the customers. The secondary business process is about supporting that, and it's about the asset management aspect of it. So from product design right through to end of life, and being able to essentially have a continuous improvement so that we can actually learn and feed back into it. And this is where the digital environment helps us greatly, because we can actually have that feedback loop automated that can go right across all of these different areas in a manner that's easily translated. So what does success look like? Well, I guess to a certain extent, we've got, over time things change and we have data, information, knowledge and experience, which helps us be aware of what options are available, what the current state of our assets are. And so it is this area here that we can use digital twinning and digital technologies to help us improve that particular area. So from that perspective, we need to actually learn how to work with digital tools to provide us with that greater awareness, so that then we can actually use that awareness to make better choices, which then can be executed into actual actions. And so those better choices, if they have a framework around it, which is around a whole of system in terms of the performance, the risk and the cost of that system, and also an aspect of whole of life, then we can actually start to leverage on that in a systematic way so that we can actually get the maximum value from our assets with a minimum risk. But there's also cautions to be had. Once we have all of our information digitized, it is actually easy for someone to look into our operation through the digital ecosystem. And so we're seeing big companies that are sort of large digital ecosystem providers, and they have access to a lot of information and data and knowledge about our operations. And so there's a bit of a, going back to that trust thing, can we actually trust them with our data, or are they potentially going to use that data and information to further their financial gains? So this is where we believe that if you're going to be managing a large asset intensive operations over a very long term, there's a need for actually an open interoperable ecosystem that is standards based, that is not beholden to a particular vendor. We can still then leverage from the efficiencies going from these digital services and the interconnections. We can actually improve our security and sovereign risk because we're not actually sending necessarily allowing others to see what our data and experience and knowledge is. We still get that improved decision making, and we maintain a digital diversity in terms of being able to maintain a healthy digital ecosystem so that we don't have a dominant player that takes over the entire environment. This will improve risk, cost, and sustainability. So within this vendor-neutral digital ecosystem, we think that the large players have a part in that ecosystem, but for them not to be the ecosystem. And in that way, we can actually maintain this digital diversity and keep the whole digital systems healthy. So this is the standard that basically has been developed and is in continuous development. It's the Open Industrial Interoperable Ecosystem. And it's a standards-based ecosystem that allows interconnectivity from multiple parties. And so we can all interoperate with each other in a digital environment as well as a human environment and leverage upon the various elements that are available. When we talk about a digital ecosystem, we start to get involved with a lot of different stakeholders. And so across this digital ecosystem, we need to have the interoperability between, say, the manufacturers of plant and equipment that are forming up the basis of our asset portfolio. And from those particular companies, we need to understand what their actual, the digital information that's associated with their particular piece of plant and equipment. So we have the OEMs involved. We also have the EPCs involved. So they have to go and build the particular asset itself. And so they need to have some information from the OEM, and they need to provide information back to the owner operators. And so we have a triangle, I guess, between the builders and constructors, the owner operators of these asset intensive operations, and all the OEMs that are supplying to both the projects and the owner operators. And I can see a time when through digital ecosystems that the OEMs will not only provide a piece of equipment, but they'll also provide the digital twin of that piece of equipment. And if it is in an interoperable environment, it means that we can just drop that digital twin into our system, if you like, and see how it's going to do through simulation and modeling without any additional work. And it's up to the OEM then to maintain that digital equivalent of the real piece of equipment. It can then be used in our construction and for our operation and maintenance in a unified whole of system, whole of life type environment. So once we've got this concept, if you like, we need to be able to transition, I guess, from pretty much what is human-based decision-making, which is based on fundamental and knowledge and experience, through to augmented intelligence, where the digital machines are helping us make better decisions, right through to ultimately artificial intelligence, where the digital environment is actually taking data in from the outside, processing it and taking action back, where there's a level of trust that's suitable for it to do that. And so we need to be able to cater for that within this digital environment. And one of the things around the AI that hasn't been done that well, although it's worked very well for marketing and stuff like that, is actually understanding what's going on behind the AI. So it's very much like a black box to a lot of people in terms of I put data in and it gives me some results out, but I can't really find out what's going on there. And this is where we're getting that merge, I guess, between data science and fundamentals, where the digital simulation and modeling and the digital twinning actually provides a context for us to actually capture both fundamental information about how things work, plus also the empirical information about the actual behavior, so that we end up with a explainable model that's not only understandable by the digital machines that have to do the work, if you like, from processing the information, but it's also understandable by the humans that have to have a trust in it. And so there's a new term that's been sort of put forward now, which is the explainable AI, which is still using all the data science, but it's also bringing in that simulation and that modeling and that fundamental element in terms of an operation, so that it provides that level of explanation and trust to the user. So this is where digital twins actually are the basis of that abstraction away from the real world that is actually understood by both the humans and the digital machines that are working on the data. And so the digital twin is a well-used term, if you like, but if we think of it just as that level of abstraction away from the real world, into a digital world in a very structured manner so that humans and machines can work with it in a collaborative environment, it sort of makes sense what the digital twin is there for. And it can be as simple or as complex as is required, depending on the complexity of the actual operation. So we can have a digital twin that's associated with the shape, the 3D form. And that's certainly in the digital engineering, there's a lot of digital design, if you like, that's going into building structures and buildings and all of that sort of stuff. And it provides that 3D form. We can also look at how that can be built in a digital environment. So you get the BIM, you go from a BIM 3D, which is the form, to a BIM 4D, which is about how I would actually construct that particular building. And then you got the BIM 5, 6, and 7D that's associated with other aspects of that form. The other aspect of a digital twin is the behavior. So this is where you start to get involved with how something actually transfers energy, for example, or how something is behaving in terms of a moving material or a process, a business process. What's the actual behavior behind that we can actually represent digitally? It could be a workflow process, or it could be an engineering process, or it could be a thermodynamic process. So it's the components that are working within my digital twin and how they behave within that environment and within the processes. The combination of that gives you the shape and the form. So from a simulation perspective, we now have a very good representation, both from a shape and a behavior, so that I can actually then start to use that simulation to do all sorts of things like operator training, like asset management. I can change the behavior of particular elements. If I was to change it from one particular component of functionality to a different component, I want to see what the impact is on my whole of system. And so you can end up with a digital sandpit, which is basically that digital representation of my operation, warts and all. So this brings me to, I guess, a concept that we use quite heavily within our business, is that of a framework, if you like, that is using simulation and modeling to basically allow us to have a systematic way of digitizing an operation, both from a design, construction, commissioning, operation, maintenance, and disposal. And so we end up with the framework, which is the real world, and in the real world, we're sensing it with observations that are digitized. That's basically the input into our digital environment. And then on the other side, we're taking action. That might be real actions in terms of maintenance actions, or changing out a pump, or operating a plant. And so there's real action that's taken in that environment. And that's the output from the digital ecosystem. Once it's in the digital thing, then all the management decisions, all the decision making, if you like, can all be handled within that digital environment. And so it's important to make sure that we actually have a very good representation of the actual world, because we're going to start to make decisions based on our digital representation. So this is where we actually use our digital twin, which becomes the actual digital replica, which can be made up of the actual theory behind how things work, if you like, and real observations about how that particular piece of equipment is working. And so we end up with this self-calibrated or self-learnt digital twin of the actual operation. And that's at an individual asset is individualized, if you like, to that to represent the real piece of equipment in the real world. Once we have that digital replica, then we can start to look at it from a couple of things. We can look for unexpected changes, which might be represent a risk. So we're looking for threats. So if the real environment is different from what we're expecting from the digital environment, that would be some sort of actionable outcome in terms that something's happened on the plant, and as a result of that, there's a threat. Or it may be that our digital replica is not representing the real world, and so we've got that continuous improvement loop that is improved understanding to make sure that our digital replica does represent reality. So we've got two corrective actions. One is plant-based and one is an understanding-based, but both of them are as a result of a disconnect between the digital replica and the real operation. We can then use a digital change agent on that digital replica to basically stimulate change. So we can look for opportunities to improve. We can try lots and lots of different scenarios, and we can use optimization to find a better way to operate, or to maintain, or to construct, or to run our business processes. And so we're looking for those opportunities in a real-time environment, and looking for those opportunities and being able to cost them, because we can actually make the change in a digital environment, find out what the change is, and then as a result of that, quantify the impact. So that's our representation, I guess, of digital twin and modelling and how it's applied in the real world. And we find that it's actually been very useful, because we can actually process a massive amount of real-time data, because if the model is saying what we're expecting and the real data is exactly the same, there's no new information in there. So we can end up processing massive amount of real-time data and only pulling out the stuff that there's new knowledge or new experience or new threats or new opportunities, and then apply it in that manner. So from basically the energy from the sun and better decision making, we believe that we can actually get an improved standard of living and reduce our consumption of resources, which is what I'm passionate about. So thank you very much.
Excellent. Thanks very much for that, Don. That was really interesting. So our speakers are now going to come together to take some questions. If you would like to ask a question, please do so via the chat box. Please make sure you provide your name and who the question is directed to. Now, to kick us off, we did receive some questions on registration, and so we're going to make a start with that. The first question comes from Stephen in New South Wales, and I'll direct this to Don. So the question is, modelling at sufficient fidelity to enhance decision-making of complex systems can be a costly exercise. So how do you evaluate the cost-benefit of modelling and simulation opportunities to ensure profitable opportunities are taken, yet costly black holes are avoided? So I hand over to Don.
Okay, thanks, David, and thanks for the question. Yeah, so it is a little bit of a black hole, if you like, in terms of you can boil the ocean or try to boil the ocean with a digital equivalent or a digital simulation, and maintaining that can become a massive problem in its own right. So we have a belief of having a framework, if you like, that allows you to capture knowledge and experience, and that's actually representative of what you're doing currently at that point in time. And so it's like a digital skeleton, and that allows you to actually know exactly where you're putting new information as it comes to hand. So if I establish a digital skeleton of the design of the game, if you like, running through the whole of my operation, and I only do it at a blueprint perspective, when I start to do the conceptual design and the detailed design and all of those sorts of things, I know exactly where that information goes to fill in my digital skeleton to start forming up my digital twin. And then as it goes through the life, we can actually draw upon that information and augment it further and further as we get more and more experience through the commissioning, through the operation and maintenance. And so it is very much a low-hanging fruit, trying to harvest the low-hanging fruit, get the value from that, and then use that experience, if you like, to be better at getting the next level. So it's an incremental, agile type of process from our perspective, rather than a massive exercise to go and digitally twin your whole operation. It's finding the appropriate spot to actually apply it, to apply the knowledge and experience, so it can be reused later on, and filling in the gaps as you go.
Okay, wonderful. Yeah, that's a really, really useful strategy. So the second question we have here is from Hassan in Queensland. This was asked on registration as well, and I'll directly this to Govinda. The question is, can you please explain how to select the right software for the monitoring of assets? And I know obviously Govinda Rockfield use a number of different software packages. So that's quite an interesting proposition.
Thanks for the question. Look, in terms of monitoring, there are a lot of software platforms available these days. But the thing is, like, a lot of them are quite suitable to low volume data. For example, if you're monitoring slope stability or things like that, you're only getting a few data points a minute or hour. So the volume is not that large. But when you look at sort of structural health monitoring, when you're sort of putting a large amount of sensors in a bridge, and if you're monitoring at 400 hertz or 500 hertz or a very high sampling rate, then all of a sudden you need a very specialized software or cloud analytics platform and visualization platform to be able to handle that volume of data. So far, we haven't quite seen a lot of sort of off-the-shelf products that is available in the market. There are quite a few proprietary tools that are available, but just watch the space. I think these things are becoming available very, very quickly.
Yeah, right. Wonderful. Okay, so the third question I'll direct to Lin. And so the question comes from Ali in Victoria, and it asks if you can explain about any industry academia type schemes that promote the application of augmented reality and artificial intelligence and so forth in industry, and how those might work.
There are a number of schemes in Australia, such as Australian Research Council. If the project contains some research elements, and they will support the industry and the university linkage project. And there are a number of other ARC centers and schemes they can support project, but normally the academic component, research component, they really need to justify. Another scheme called Corporate Research Center, CRC, they have like a project level or program level. So project level is easier. They have a 2 application round each year, so that the industry can put in some fund, and the CRC from government can support like a 1-to-1 things. For technology side, there are a number of sort of a local government. They support innovation, and industry domain like power transmission. They have their own research group that can support some of the project. Really depends on how much funding and what the scope of the project do you need. Hope this is helpful.
Yeah, great. Thanks, Lynn. That's excellent. So the next question I've got here comes from Vincent in New South Wales. I'll direct this at Don particularly. And so the question's, can your approaches or the simulated asset management type approach more generally, I guess, assist with compliance to ISO 55000, and how might that actually kind of complement that?
Yeah, so I guess the concept of ISO 55001 is asset management, but having that real relationship back to the business strategies, the asset strategies, and then the asset management plans out of that. And what we see is this modelling and simulation methodologies, if you like, allows us to have that line of sight now between, I guess, the business strategy or the business purpose, going through the business strategies, through the asset management strategies, through the asset management plan, right through to actually people taking activities down on the physical assets. Because we can actually model it, and we've got the ability to I guess have that line of sight. What it does is it allows us to not only get better compliance, if you like, with the ISO 55000, but we can actually run those different scenarios as a whole of system, whole of life type of basis, so that you can actually look at the benefits associated with coming up with good asset management strategies and having good asset management plans, because you're actually playing them out in the digital environment and seeing what the impact is from the value to the business and whether it's actually meeting the business strategies. So we see that modelling and simulation and particularly the ability to look at the whole of system, you can actually break down the traditional silos that typically exist within asset management, which is your production and your maintenance, and there's always a bit of an argy-bargy there, if you like. Whereas once you get into a model, you can actually quantify exactly what a change in maintenance strategy is going to have on a production, say, for example, or what changing the level of production or how hard I'm running the plant, what impact that's going to have on my asset consumption and my asset life and my maintenance requirement. So we see that there's two elements there. There's the compliance element, and then there's the ability to actually get certainty that strategy and those plans are actually going to meet the business objectives.
Yeah, right. Okay, that's great. Okay, so moving on to some of the live questions that we've had. So this one comes from Ellen and is directed at Govinda. And so Ellen's interested in what kind of data you're collecting from the sensors at the top of the power pole, so the Lixia sensors. What type of data are you collecting? And I'll probably add to that, and how are you processing that data to give you asset management kind of outcomes?
So there are a few things in there. So we've got a 6-axis accelerometer there. So it sort of collects data on sort of tilt, pitch, and roll. So those are the primary sort of data that we collect out of those sensors. But we also collect the acceleration trace, if you will. So what that would do is like with the by sort of turning that one into sort of a frequency domain, you can look into the degradation of that over a period of time. So if your butt is degrading over a period of time through some sort of termite attack or rotting or something like that, we believe that it will start to pick that degradation. So that is something that you can use as part of a predictive tool, and you can also use AI on top of that by fusing other data sets to provide insights as to how your structure is degrading over a period of time as well. And another element to that one is it's got a camera in there as well, so it just looks for the sag of the conductor line. So if you are worried about whether your conductor line clearance from ground or from structure is compliant or not, so the camera can give you that through image recognition techniques, can give you that insights as to what the height of the conductor line is at as well. So those are the key sort of structural serviceability related data that you can get out of those sensors on those pole top sensors.
Yeah, right. Okay, that's really interesting. Very, very Internet of Things and kind of in kind of connected to themselves. Hey, that's really, really interesting. Okay, so I've got another question here from Yemi, and it's directed at Professor Ma. And so Yemi's interested in to what extent you're using analog data in the data mining, or whether it's sort of predominantly sort of more digital based data.
Yes, thank you for the question, Yami. In the past, we all have to convert the analog data into digital data to do analysis, but not anymore. Nowadays, the hardware is no longer the limitation factor for doing analysis, because you do have a different big data technology you can dealing with various of data. Apparently, I do not do that myself. There are researchers doing that. We haven't found too much limitation in that aspect. It depends on how do you want to use the data. The key is that how fast, how quick, or how accurate you could make sense of the data. That depends on the algorithms and the expert knowledge, how much you have. Thanks.
Great, thanks, Lynn. Okay, so I've got another question here to Don, and it comes from Rashan. And so Don's asking, in your experience, Rashan's asking you, Don, in your experience, to what extent is model-based system engineering used for requirements, specification, verification, and validation work as opposed to a static document?
Yeah, thanks, Rashan, for that question. Not enough, I guess, is the answer to the question. We're not seeing enough model-based systems engineering being used to actually define the specification. Because if we did, and this is where I believe we should be doing a lot more of this, if we were to actually use model-based systems engineering as the basis of defining the specification, we can actually validate the impact of that specification through the whole of life in a modelled type basis. And what I mean is, like if we were specifying a particular piece of equipment that is made up of multiple components, and we're specifying it at that component level. So if you look at it from a functional location, I'm specifying the requirements for that particular piece of equipment. Once I've done that, it's already in the form that I can actually test, not only when I'm procuring the component, whether it's going to meet or exceed my specification, and what are the differences between what I've specified and what the theoretical performance of that piece of equipment is. But then through the life cycle, I've already got it into the form that allows me then to check, so I've got the specification, then I've got the design of the piece of equipment that I've actually procured, then I've got the commissioning, which can test it against both the specification, the original specification, and what was supposed to be provided by the vendor. And then you can start to go into that verification in an automated manner so that you can cover lots and lots of different aspects of an operation, from the specification through to the verification and the quantification of any differences. So yeah, we believe that it should be much greater take up rather than staying with the static type documentation and building a big heap of wordy documents around what's been specified, which then has to be interpreted, if you like, before you can actually go and test it, for example, or see what the impact is from the rest of my operation. So yeah, not enough is being used in that area, but we believe it's a good opportunity for improvement.
Yeah, absolutely. Yeah, excellent. All right. Okay, so another question directed to Govinda from Richardson. In what way would you recommend incorporating the effects of corrosion in finite element modelling and simulation? I think we had a second question about modelling of corrosion in steel structures later from Carlos, and I guess corrosion is one of those wildcards that's a little bit challenging to implement in any model, let alone a more asset management long-term strategy. So I guess, would you like to comment more broadly on how you do corrosion in that sort of context, Govinda?
Thank you very much. Thank you both. It was a very interesting question, that one. And obviously, when you take a very simplistic approach, modeling corrosion into your, it's quite challenging. But if you take it to a more sort of like a 3D modeling approach, then all of a sudden you got that ability to actually sort of locally reduce the thicknesses of the plates and all that. And the ability to do that one is really important, because in certain instances, like if the corrosion is not in a critical area, so even though you've got a significant corrosion, so it sort of may not have any significant impact to the performance of the structure or the asset. But even if you've got a small amount of corrosion, but if it is in a highly stress concentrated area, such as connections, and obviously you've got a pretty significant impact on the fatigue performance of the structure. So the ability to be able to really sort of fine tune the modeling of the corrosion loss through the actual field measurement data is really powerful, and that is how sort of it's typically done when you do the assessment at a much higher tier level.
Yeah, right. Great. That's really interesting. Okay, so I'll direct this question to Lin, and it's coming from Rashan. And so Rashan's asking, what challenges are there in joining models, including potentially legacy models, to get kind of a holistic integrated one? And I would have thought this was kind of an area that may be worth commenting on from the whole panel. So Lin, we might start with you, and then we can move on to the other two as well, because there's an awful lot of legacy simulation software out there that has a tendency to be pretty industry standard in a lot of contexts. And how do you integrate that with a newer, more modern approach to these types of things?
Yeah. Okay. This is really a good question, but it's quite broad. Depends on the legacy model and the holistic model, what we want. So if the legacy model is mainly for process control and alarming, that's very different from the subsystems health and health prediction. If this is only the for the alarming, for a certain sort of operation failure states, then it is less useful for the holistic integration model. But we need sort of the whole process, the whole the conditions of the whole process of each legacy model to be able to tell the holistic one. And I think that is the first challenge I would have. And as David said, it is a big question and involve lots of other expertise. But however, if we do like the example I gave in the presentation, that we already have very good simulation model, physical model in the heat exchanger. So that really make whole things much easier. But the simulation model itself could be a challenge as well. To summarize that, from component or subsystem to system level is not easy, but we have done quite a number of those projects. Depends on what we want, is at the decision level. Sorry, I sort of feel difficult to answer straight away.
Yeah, it's a very, very challenging question. I think one that a lot of people are sort of thinking about. So, I mean, on that topic, Govinda, in terms of a lot of the modelling that certainly I know Rockfield does, there's a lot of finite elements and that kind of stuff. And how easily does that integrate with things like the more AI-based approaches that you're taking? Is there an elegant way of doing it, or is it more sort of have some finite elements and use that as an input in sort of a two-stage process, or are there other approaches that people might be able to look into?
All good. So what we're finding is one of the more sort of mainstream, or some of the mainstream code providers. They've really put a lot of effort into developing or integrating AI into modeling. So which is really powerful. But coming back to the original question around sort of the legacy models and how we sort of integrate that one into sort of holistic framework, what we're finding is that like in the 3D sort of like a basic 3D modeling point of view, there are sort of native formats that sort of models can be sort of converted from one format to another format. So that has really changed over the last little while. So at least from the physical shape of it, it's really easy to convert them into a different format. And also these days the final element modeling tools, their preprocessors are becoming really powerful as well. So you just don't have to spend as much time as we used to do, like several years ago. So things are becoming quite powerful, and the whole thing around sort of with the additive manufacturing and all that type of thing. So the AI is really now sort of taking off when it comes to final element modeling as well. So which is really interesting to see, and really looking forward to see how things develop moving forward.
Yeah, absolutely. It's a really interesting space, and you can see a lot of the software kind of developing at a rate that it perhaps hasn't been developing for quite some time, which is really exciting. Don, I guess on the same kind of topic, do you find that your more sort of game engine approach to building around the assets, are you integrating a lot of more conventional tools, or are you kind of developing the tools with the engine itself?
Yeah, no, we're certainly integrating into the existing knowledge. So I guess legacy models have a lot of knowledge encapsulated in them, and so it's a matter of actually getting alignment, if you like, in terms of almost at the decision level. Well, what's this model trying to tell us in terms of a legacy model, and where's that fit into my maybe more holistic type of modeling framework? And we certainly use system-based engineering and building the system boundary and what's happening at that system boundary to try and encapsulate, I guess, the information that's contained in those legacy models, and then being able to provide that, if you like, as an interface into the more potentially a more comprehensive whole of system type model. So you're componentizing up the legacy models and incorporating them maybe from a different context into your more holistic type model. And also just in terms of when you start talking about real-time modeling, it's the ability to actually be able to run these models in real time to augment the other analysis and other modeling that you're using potentially for different areas. The one thing that we, I guess, try and focus on, if you like, is that every model is wrong, but some models are useful. And so it's actually making sure that when you start getting these integrated models starting to work, you actually have a level of uncertainty that comes in with the model, so that you can actually start to do a couple of things. You can actually have multiple models working on the same problem, so that can give you increased certainty of an outcome, just because I'm actually modeling it in two different ways. And if both models are suggesting the same thing, then that's going to be more powerful than just an individual one, and particularly where there's a disconnect, if you like, between the two models. But having that uncertainty also incorporated in the outcomes from the model allows you to actually make a valued decision and weighting, if you like, of which one I'm going to err towards. Because as assets degrade, if you've got a static model, then the uncertainty of a static model compared to an asset degrading might slowly get worse, and so you might want to put less emphasis on that than perhaps one that's a self-learning model that's continually updating itself and continually understanding the behavior. So that's where the uncertainty can come in, where I can run those two models. It's just one slowly gets worse compared to the other, and then I can actually still use it as part of my multi-model environment and leverage off the experience and knowledge that's captured in that model.
Yeah, right. Wonderful. Okay. So I think that's a really nice note to kind of finish our session on. So I'd really love to thank all of our speakers here in this session. It's been a really, really interesting one, I know, for me, and hopefully all of our viewers as well. So can everyone please join with me again in thanking Professor Lin Ma, Dr Govinda Pandey and Don Sands for their time and really valuable insights on this topic, and hopefully everyone can take a little bit with them into their own practice. I'd love to thank Engineers Australia and also, as the industry partner, Queensland University of Technology for making this webinar possible. And obviously, we'd really appreciate your feedback on the program today to help us improve and plan future sessions. So if you could please complete a short feedback form, which is linked in the description box below, that'd be really, really helpful. So thank you again for joining us, and we really hope to see you at the next webinar. Thanks very much.